Welcome to module 7. In this module, we will discuss the concept of independent events. So first, let me give the definition of independent events. Suppose you have n events E1, E2, En. Now these events are said to be pairwise independent. If you look at the probability of joint occurrence of any two of them, that is same as the product of probability of occurrence of individual of them. So that is what a pairwise independence. So that means probability of joint occurrence of any two of them is same as the product of individual probabilities. I call them as mutually independent if you take the joint occurrence of any subcollection of E1, E2, En. So this is what the probability of any subcollection of E1, E2, En, because D1, D2, Dk are from 1 to n, they are distinct. So I look at the probability of joint occurrence of any subcollection of E1, E2, En. That is same as the product of individual probabilities, and that should happen for every subcollection of E1, E2, En. So how many subcollections are possible? I leave out subcollection of singletons because that would be automatically satisfied. Probability of E is same as probability of E. So how many such conditions would be there? NC2 plus NC3. So this would be conditions when you are talking about taken two at a time, joint occurrence of two events taken at a time, then joint occurrence of three events taken at a time, plus finally joint occurrence of all events taken at a time, which would be basically probability of E1 intersection E2 intersection En. So these are the total number of conditions you will have to satisfy for mutual independence, and this is nothing but 2 to the power n minus 1. So let us see the following observations. Note that mutual independence is much more demanding because it is saying you look at any subcollection of this, the probability of joint occurrence would be same as probability of individual, product of probability of individual events. Whereas pairwise says that you only look at in the pairs. So certainly mutual independence implies pairwise independence, and that is what is said over here. Mutual independence implies pairwise independence. So if events E1, E2, En are mutually independent, they would be pairwise independent. Now the question is whether converse is true. Whether I can say if E1, E2, En are pairwise independent, can I say that they are mutually independent? And the answer is no, as the following example suggests. So let us take my sample space to be 1, 2, 3, 4, and suppose since my sample space is finite, it is enough to know the probability of singletons, because probability of any subset of E then I can get through probability of singletons. And suppose all of these outcomes are equally likely. So P of I is 1 by 4, I is equal to 1, 2, 3, 4. So this is a proper probability function because probability of whole omega is probability of union of these EIs, each of them is 1 by 4. So 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, which is 1. Probability of any A you can get it through probability of singletons. So now I define events E1 as 1, 4, E2 as 2, 4, E3 as 3, 4. So all of them have one element 4 common. Let us look at what are their individual probabilities, because number of, so probability of E1 would be 1 by 4 plus 1 by 4 because it has two elements 1 and 4. So probability of 1 is 1 by 4 plus probability of 4 is 1 by 4. So 1 by 4 plus 1 by 4 is half. So each of them similarly probability of E2 is half, probability of E3 is half. Now let us look at E1 intersection E2. What is the E1 intersection E2? E1 intersection E2 is a singleton set 4. Since all of them have only one element in common, that is the same element 4, so probability of E1 intersection E2, probability of E1 intersection E3, probability of E2 intersection E3 would be same as probability of 4, which is same as 1 by 4. So what you see is this is clearly same as probability of E1 into probability of E2 because each of them is half. So the pairwise independence is obvious from here. So this pairwise independence is clearly there. Now to see the mutual independence, I have to satisfy some additional conditions. What are the, so 2 taken at a time I have done. Now I look at what is the probability of 3 taken at a time. So probability of E1 intersection E2 intersection E3. But all of them have only one element common, which is 4. So this is same as probability of 4, which is 1 by 4. So if these events were mutually independent, this probability should be equal to probability of E1, probability of E2 into probability of E3, if they are mutually independent. So that is a big question mark. But that doesn't happen because this is 1 by 4, and if I look at probability of E1 into probability of E2 into probability of E3, that turns out to be 1 by 8. So this is an example where you see that events E1, E2, E3 are pairwise independent, but E1, E2, E3 are not mutually independent. Now let's look at some useful remarks. Events in any subcollection of independent events are independent. That is trivial, because to show that I consider any subcollection of, for example, if there were E1, E2, E3, they were independent. I consider, let us say E1, E2, E3, E4 were independent, and if I consider E1, E2, E3, a subcollection of them, to see that they are independent, what I have to do is I have to look at any subcollection of this. For that, probability of joint occurrence should be same as product of individual probabilities. But any subcollection of this is also a subcollection of this, and this is independent. This collection is independent. So probability of joint occurrence would be same as individual product of individual probabilities. So this observation is obvious, that any subcollection of independent events are independent. Now let us look at a question. Suppose you are given a collection of independent events, E1, E2, En. What I do is I convert some of EIs into their complements. Then whether the resulting collection of events is also independent. And the answer is yes. To see that, let us see the following simple observation. Suppose E1, E2, En are independent events. I look at k of them, and to begin with I make one of them as complement. Because if I make one of them complement, and this probability of joint occurrence still remains the product of probabilities of these events, then I can say that I can make second complement also, and by induction then I'll be able to say that if I put any number of them to be complements, the probability of joint occurrence would be same as the product of individual probabilities. So let's see first if I make one of them as complement. Now you know that probability of A is same as probability of A intersection B plus probability of A intersection B complement. Right? This is what theorem of total probability says. So probability of A intersection B complement can always be written as probability of A intersection B minus probability of A. So I take this whole as A, this as B. So A intersection B complement is same as, sorry, this should be, this A intersection B complement turns out to be probability of A minus probability of A intersection B. So A intersection B complement turns out to be probability of A minus probability of A intersection B. So this is A intersection B. But E1, E2, En are independent, so probability of any joint occurrence of subcollection of them would be same as the product of this probability, individual probability. So that is what is coming over here. Now this is also a subcollection of E1, E2, En, so probability of joint occurrence would be same as product of individual probabilities, because E1, E2, En are independent. So product of them can be written as product J is equal to 1 to K, P of Eij, and then P of Ei. Now this is common, so J is equal to 1 to K, P of Eij, 1 minus P of En, but 1 minus P of En is same as P of En complement. So I say, what I saw is, if E1, E2, En are independent, if I consider the probability of joint occurrence of some of them and I make one of them to be complement, still I get the product of probabilities. I can make it 2 by induction now. Still I'll get the probability of joint occurrence as the product of probabilities. So this observation suggests that if you have a collection of independent events, you can make any number of them to be their complements, and the resulting set would still be a collection of independent events. So that is what it says. If E1, E2, En are independent, you make some of them as complements, then that collection itself is a collection of independent events. In particular, for example, E1, E2, En are independent, I can make all of them also complements. That collection is also a collection of independent events. Now sometimes we say that 2 random experiments are performed independently. What it means is the associated events are independent. That means events of the 2 random experiments are independent. Now suppose that probability of E1 is greater than 0. Then we know that E1 and E2 are independent. if and only if this happens. That is a definition, which is same as probability of E1 intersection E2 divided by probability of E1 is same as probability of E2. But this is same as probability of E2 given E1, conditional probability, which is same as P of E2. So my definition suggests that if E1 and E2 are independent, if and only if the conditional probability of E2 given E1 is same as the unconditional probability of E2. Or in a sense that the conditional probability does not change when you have additional information that E1 has occurred. Or in other way, E1 is having no effect on the occurrence of E2. So this justifies the way we have defined the independence, which is E1 and E2 are independent if probability of E1 intersection E2 is same as probability of E1 multiplied by probability of E2. Now another simple observation is that if E1, E2, and E are independent, you consider disjoint collections of them, you apply any operations in them, union, complements, they would also be independent. So that is what is happening. If E1, E2, En are independent, E1 complement, E2 union, E3 complement, union, E4 are independent. As long as E1 is not over here and you are considering any sets leaving E1 and applying any operations, union, intersection, complements, that would also be independent. This can be proved. So I give this as an exercise. Similarly, E1 union, E2 complement, E3 complement, this doesn't have anything common from E1 and E2. And E4, E5 complement, which doesn't have anything common from E3, E2, and E1, they would also be independent. Now let me give this small quiz. Let E1, E2, E3 be independent events with probability of EI as 1 upon I plus 1 for I is equal to 1 to 3. Find the value of probability of E1 union E2 complement union E3. So take this as a quiz for today. Now let me give you take home problems. Let En be a sequence of events. Now these are infinite collection. I have defined the independence for finite collection. So infinite collection of events is said to be independent. If you take any finite subcollection of them, that forms a collection of independent events. So that is what the definition is. If that happens, try to show this. Probability of union EI is greater than or equal to 1 minus e to power minus summation I is equal to 1 to n probability of EI. I would suggest that use the inequality that e to power minus x is always greater than or equal to 1 minus x. And then use the Boole's inequality. Using this, try to prove this. That if summation I is equal to 1 to infinity probability of EI is infinite, then probability of intersection EI complement is 0, which is same as saying that probability of union I is equal to 1 to infinity EI is 1. So try to do this exercise. Now let me give the abstract of the next module. So many times what may happen is I may not be directly interested in my probability space P omega P. I may not be interested in this space directly. Rather, I may be interested in some numerical aspect of this space omega. For example, if you are tossing a coin twice, I may not be interested in the sample space which is HT, TH, TT, and so on, HH. Rather, I may be interested in some numerical characteristic of this omega, which for example in this case would be I am interested in number of heads observed in 2 tosses. So what I am interested that means is a function omega which is real valued. And such functions are called random variables. So we'll introduce the concept of a random variable in the next module. We'll study various properties of a random variable and how they are random in certain sense. So this was all for today's lecture. Thank you for your patience and have a great day.